I'm Bastien. I'm from University of Evansville, and I'm presenting some results Dr. Kamali and I found on link-irregular graphs. Basically, link-irregular graphs are a special, very recently defined family of graphs, and they have some really interesting properties as we'll get into. So let's start with our basic definitions. Take a graph G. The length of a vertex in G is as defined here. So basically, pick the vertex, we'll call that V, right? So what we'll do is we'll take the neighbors of V, highlighted here in orange, as well as the edges between those neighbors, kind of a dark blue, and you get rid of everything else. That's the length of V. So what we're interested in is if no two vertices of a graph G have the same length, then we call G link-irregular. Do these exist? Yes, they do. The authors Ali, Chartrand, and Zhang, in their paper introducing the topic, provided this example to show that, in fact, link-irregular graphs do exist. As you can see, the links are listed right here. No two of them are isomorphic, so it's a link-irregular graph. In fact, in their paper, they proved that there are infinitely many link-irregular graphs. The proof is they're rather long, about 2 pages, I think, but we'll give like a brief overview of how that proof works. So you start with the link-irregular graph on 6 vertices they have found, and then to a vertex of minimum degree, we'll just pick this one of degree 2. You add a pendant edge. And then that's a link-irregular graph on 7 vertices now. After that step 1, now we do step 2. You add a vertex, attach it to every other vertex in the graph, and that's another link-irregular graph, this time on 8 vertices. And then we repeat that process over and over and over again, and inductively we have infinitely many link-irregular graphs. So there are quite a few of them. It's certainly worth studying. So like with any new concept that there's not a whole lot of results on, you start with just toy around with the concept. What is link-irregular? What's not link-irregular? So to find some basic results about the nature of these graphs, we'll use this result mentioned in the paper I discussed earlier. If G is a graph, then some pair of vertices must have the same degree. What does this tell us? Well, the girth of any link-irregular graph is 3. To see this, imagine that we have 2 vertices, U and V. Pick any graph, any link-irregular graph. We have 2 vertices, U and V, right? And they have their own neighborhoods. Now, since we're assuming these are the vertices of same degree in G, that is. Now, since G is link-irregular, they must have distinct neighborhoods. So at least one of these neighborhoods must have an edge. So then that edge, with whatever vertex has that edge, forms a triangle. So since G has a triangle, its cycle of minimum degree is 3, which is the definition of girth. Therefore, any link-irregular graph has a girth of 3. That's basically just what I'm saying here. So what does this mean? Well, for one, no tree is link-irregular. In fact, no forest is, because by definition, a tree is a connected acyclic graph, and a forest is an acyclic graph. So can't have a 3-cycle in a tree or forest, so it can't be link-irregular. We also have no bipartite graph is link-irregular. It's a well-known result in graph theory that any bipartite graph has no odd cycle. Well, if it has to have a 3-cycle, then it can't be bipartite. So following those basic observations about what a link-irregular graph has, properties of it, and what it can't be, we move on to questions about bounds on the edges. So if a graph has fewer than this many edges or more than this many, then that means it's not link-irregular. We want to find such a bound, because that might be easy to discard certain graphs when we're looking at link-irregular graphs. So first we'll start by developing an upper bound. So a link-irregular graph on n vertices can have at most 1 vertex of degree n minus 1. Any 2 such vertices have isomorphic links, and at most n over 2 vertices of degree n minus 2. This is a result we proved in our paper. It's a fairly simple counting argument, and it just shows that if you have more than n half vertices of degree n minus 2, then 2 vertices must have not just isomorphic but identical links. So we derive this equation here. It's a rather long equation, but what it's saying is simple. the number of edges is less than half the sum of degrees of the vertices. That's the degree sum formula, which is half the degrees of the vertices. We have at most one vertex of degree n minus 1, at most n half vertices of degree n minus 2, and the rest have degree at most n minus 3. So that's all we're counting, and we develop this quadratic form for the maximum number of edges on a Link-Irregular graph on n vertices. This is a fairly decent bound. It's linearly less than the maximum number of edges on any graph. So it cuts out a sizable portion of graphs saying these graphs cannot be Link-Irregular. Now, before we move into developing a lower bound, this is just a helpful piece of information. So on the online encyclopedia of energy sequences, lists the number of isomorphism classes of graphs on n vertices, one graph on 0 vertices, one graph on 1 vertex, 2 graphs on 2 vertices, and so on, right? And that'll be helpful in counting a lower bound for a Link-Irregular, the number of edges in a Link-Irregular graph. All right, so there's at most one vertex of degree 1 from that sequence, 2 vertices of degree 2, 4 vertices of degree 3. So then, using a similar formula as before, we find the lower bound any Link-Irregular graph has more than this many edges, but since it has to have an integer number of edges, you can't have half an edge. The number of edges is greater than or equal to 2n minus 5. Now, you may notice right now, wait a second, we're assuming that we have at least one vertex of degree 1, 2 of degree 2, and 4 of degree 3. That's 7 vertices. But we showed earlier a Link-Irregular graph on 6 vertices, right? Well, there's only one Link-Irregular graph on 6 vertices. It's the Link-Irregular graph with the fewest vertices, and just testing it with that formula, it holds. So this formula, in fact, holds for all Link-Irregular graphs. And that's why we don't go farther, too, because after 6 vertices, you get a lot more Link-Irregular graphs, and you'd be cutting out a lot to go further. So these are the bounds that we have on the number of edges in the Link-Irregular graph. They're pretty nice bounds, but if we think asymptotically, we could go a bit farther than that, right? In particular, the lower bound, right? So right now, the lower bound is on the order of n. We want maybe something a little bit stronger. So using basically the exact same method, slightly modified and taken asymptotically, we find a lower bound on the order of n squared of log n. So that's a better lower bound than on the order of 2n. So it strengthens the lower bound we have when we think asymptotically. This result you can find on the paper that'll be on archive pretty soon once they process it. So now let's move on, right? So we have these edge bounds, but what are they useful for? They're interesting in their own right, but what can they tell us? Well, one fact of graph theory is that any planar graph, as a graph that can be drawn on the plane so that no edges cross, must have at most 3n minus 6 edges, all right? So applying our results on edge bounds, similar results, you're just extending the results, right? You could find that a Link-Irregular graph with 208 or more vertices have more than this number of edges. It's not a very neat number, but then using that, you can find if n is greater than 277, this number of edges is more than the maximum number of edges in a planar graph. So really, the only Link-Irregular graphs that could possibly be planar have fewer than 277 vertices, which means that we only have finitely many planar Link-Irregular graphs. It is non-zero because the initial example we showed on 6 vertices is planar, but still, all but finitely many Link-Irregular graphs are non-planar. It says we have infinitely many Link-Irregular graphs. That's quite a few. And that's just restating our result that we had earlier. In fact, so I want to strengthen this result, right? Is there any maybe smaller class of Link-Irregular graphs where it strictly holds? We don't have to limit the number of vertices. It's just no such Link-Irregular graph is non-planar. Well, if there were to exist any regular Link-Irregular graphs, then no such graph would be planar. We found this result. It uses like just degree by degree, degree by degree counting of the results, but it's a nice result. Any regular Link-Irregular graph, no matter how many vertices it has, will not be planar. Any regular Link-Irregular graph will not be planar. And on that topic, do these exist? Well, that was the topic of a conjecture by, once again, Ali, Chartrand, and Zhang, the authors of the paper introducing the subject I mentioned. They conjectured there exists no regular Link-Irregular graph. Makes sense, right? Like, kind of regular and irregular in the same sentence, right? You'd think like they're diametrically opposed. There's no such way that they could be, a graph could be both. But since link-irregularity is a weaker condition than irregularity, we found a counterexample to the conjecture. If you care to count, this is a 12-vertex graph with 7, each vertex is degree 7, so it's a 7 regular graph on 12 vertices. In fact, it's link-irregular. Here are the links of each vertex to make it a bit easier to check the link irregularity. Here are the degree sequences. So the link of vertex 0 and the link of vertex 6 are the only 2 links that are the same in this list of degree sequences. If you go back and check these, look closely at them, you can just count the incidence relations on the vertices, and you can verify that these 2 links are in fact different. So no 2 links are the same. So this graph is a regular link-irregular graph, which disproves the conjecture that Ali, Chartrand, and Zhang made. All right, so is their result maybe true with a weaker hypothesis? We show that there exists no regular link-irregular graph on n vertices for n is less than 10. So a lot weaker than their conjecture, but it's the strongest we've been able to prove, and like as they showed, for 12 vertices, their conjecture is wrong. Okay, so clearly you can't strengthen our weaker result a whole lot. And this leads into the question, all right, so we have a regular or link-irregular graph on 12 vertices. How many are there? Well, using probabilistic methods, we found that there is a very high probability for regular link-irregular graphs on any large enough n. So it seems like there could be quite a few of them, which actually leads us into our next conjecture. So Dr. Kamali and I, we've conjectured that there exists a regular link-irregular graph on n vertices if and only if n is greater than or equal to 12. This is supported by our probabilistic arguments that we mentioned before, as well as just some results that a computer spit out. It seems like a likely conjecture. And we're going to end on that conjecture. This is the one source, since it's the one paper written on the subject prior to us. And thank you all for your attention.